Potentiometer, calibration of a high range voltmeter. Aim of our experiment is to calibrate a given high range voltmeter with the help of a potentiometer. When we are using a potentiometer for the calibration of a high range voltmeter, we are coming to the theory part. Initially, when we are connecting a Daniell cell of EM of 1.08 in the secondary circuit, and if you obtain L as the balancing length, then the potential difference per unit length of the potentiometer wire is 1.08 by L. Now, in the secondary circuit, instead of the Daniell cell, we are connecting a Ohm's law resistive circuit, and two resistance P and Q are connected, and a voltmeter is connected across P and Q. Then the voltmeter reads the voltage across PQ. Then we can write a relation P plus Q divided by P. That means if you are selecting P and Q such that, for example, let P is equal to 10 and Q is equal to 90, then P plus Q is 100 divided by 10, that is equal to 10. That is same as potential difference across P plus Q divided by potential difference across P. That is from the principle of potentiometer, or here we are considering the current flowing through P plus Q and the same current is flowing through P. So P plus Q into I, that is divided by P into I, is same as P plus Q divided by P, and that we obtain 10. So this is the arrangement what we are doing here. Then the potential difference across P is equal to 1.08 by L into L1. That means we are connecting a galvanometer across P, and the potential difference now here in the secondary, potential difference across P is introduced in the secondary circuit, and if L1 is the balance length, and then the potential difference across P is equal to 1.08 divided by L1, because 1.08 by L is the potential difference per unit length. Then from our earlier formula, if we obtain the potential difference across P, then the potential difference across P plus Q should be equal to 10 into potential difference across P. Potential difference across P plus Q should be equal to 10 into potential difference across P. So we are getting the potential difference across P plus Q is equal to V, that is equal to 10 into 1.08 by L into L1 volts. Remember, that is the potential difference across P plus Q. But in the voltmeter we can read the potential difference across P plus Q. So that voltage measured by the voltmeter is taken as V0. So V0 is the voltage measured across P plus Q, and the voltage across P plus Q is calculated using the formula V is equal to 10 into 1.08 by L into L1 volts. Then we can calculate the difference between the voltage V and the voltmeter reading, that is V minus V0 is calculated, and that is the correction in the voltmeter. Now the experiment is repeated for many times for different values of V or V0, the observed V0 value. So coming to the procedure part, first part is standardization of the potentiometer. For that, we are connecting a Daniell cell having a 1.08 volt in the secondary circuit, and let L be the balancing length. Then 1.08 by L is determined, that is potential difference per unit length is determined, that is the standardization of the potentiometer. Then as we mentioned, we connect the secondary circuit to resistance P and Q such that P plus Q is 100 is connected, and a voltmeter is connected across P and Q, and a potential divider arrangement is here using a rheostat and a voltage source in the secondary. We can vary the current through P and Q. That means the potential difference across P and Q can be changed, or the potential across P is changed. Now when the potential across P is changed, we can give the jockey contact some point so that the voltmeter reads a certain value, say 1 volt. So initially it is adjusted such that the jockey is given contact at some point so that the voltmeter reads 1 volt. Then we calculate obtaining the balancing length. We calculate the value of V using the formula V is equal to 10 into 1.08 by L into L1 volts. Now the experiment is repeated by moving the jockey to some other point such that the voltmeter reads 2 volt. In that case also we obtain the balancing length, and the corresponding voltage is determined. The experiment is repeated for moving jockey so that the voltmeter reads 3 volt, 4 volt, 5 volt, 6 volt, 7 volt, etc. because it is a high range voltmeter. The voltmeter readings are high 1, 2, 3, 4, 5 etc. volts. Now this is the tabular column that we are using. Initially we are finding the balance length for the Daniell cell. So potential difference per unit length of the Daniell cell 1.08 by L is calculated. We mentioned we are taking P10 and Q90 such that P plus Q by P is equal to 10. Then the voltmeter reading 1, corresponding balance length is L1. So the balance length is adjusted such that the voltmeter is reading 1. Then we calculate the voltage V. So that voltage is somewhat near to 1 volt. Then V minus V0 is calculated. Then the balance length is changed, or the jockey moved such that the voltmeter reads 2, 3 etc. up to 8 or 9 volts. Then a calibration graph is plotted between V0 along the x-axis and V minus V0 along the y-axis. So a calibration graph is plotted, or the given voltmeter is calibrated. Now when we are using a potentiometer for the calibration of a high range voltmeter, let us see the experimental setup. We are provided with the potentiometer. The potentiometer consists of a uniform wire which is kept between two terminals A and B. Here it is kept in 10 rows. So total length is 10 meter for the potentiometer wire. Between A and B we are having the primary circuit. Now from the terminal A, the positive of a battery is connected. Now from the negative of the battery, a key is included in the circuit. From the key, a rheostat is included. Now from the rheostat it is connected to B. So that is the primary circuit. By varying the rheostat, the current through the potentiometer wire can be changed, or the potential across the potentiometer wire can be changed. Now in the secondary circuit, from A, we are including initially a Daniell cell. Now here this would be a voltage source. This source is having a provision to provide the Daniell cell voltage, that is 1.08. So it is connected between the positive and negative. Now a galvanometer is included in the circuit, and also a jockey is included. Now initially we want to find the balance length corresponds to that Daniell cell. Now for that, the jockey is given contact on the potentiometer wire. Initially on the first row we are getting some deflection in the left side, and then we are giving the contact on the last row, or towards the end B, then we are getting a deflection on the right side. Now we have to find out at which point we are getting the zero deflection, that is the balancing length or balancing point. Now here somewhere here, now we are getting zero deflection. On the above row the deflection is on the left side, below it is on the right side. Now moving here, at this particular point the deflection is 0. Here I am getting that value for balance length on the scale, that is we can measure here, the point corresponds to 720. So the balance length for the Daniell cell is 720 centimeter. So that is the first part of the experiment. Now don't disturb the rheostat in the primary circuit, don't change the current in the primary circuit. Now we are going to change the secondary circuit. We are going to introduce the resistances P and Q and the high range voltmeter as we have seen in the theory part in the secondary circuit. Now the connections are changed. In the secondary circuit we are connecting two resistances P and Q in series, and across PQ the voltmeter is connected. Now from P it is connected to a potential divider arrangement with the help of a rheostat. It is connected to a secondary voltage source. Now this is the resistance P, and the resistance of 10 ohm is unplugged in P. Now P is connected to Q. From Q the rheostat is connected. Now rheostat is connected to key, and then the voltage source is connected, the positive is connected. So that is the secondary circuit arrangement, and here a galvanometer is connected from P through a jockey J, so that we can give contact at any point on the potentiometer wire. So that is the experimental arrangement. We have done the experimental arrangement here. Now the key in the secondary circuit is inserted. Now we can see a voltmeter reading that we can change with the help of the rheostat. Now initially the rheostat is adjusted so that the voltmeter reading is 2 volt here. Now we want to find the balance length. We are giving contact on the first row, left side deflection. Say in the right row, right side deflection. Now we are trying where we are getting a 0 deflection. Now here, somewhere here we are getting a 0 deflection. Now the deflection is 0. Here it is left side, on the next row it is right side. At this particular point we can see 0 deflection. Now here it corresponds to a value of, we can take the reading here. Now I am getting a reading of 140 here. So for a voltage of 2 volt, the balancing length is 140 centimeter. Now we want to repeat. For that we can change the rheostat so that the voltmeter reads a value of 3 volt. Now rheostat is moved, the voltmeter reads a value of 3 volt. Again we are moving on the wire to find out where we are getting a 0 deflection. Now it is moving to 0, now approximately 0, now it is coming to a 0 value here. Now it is 0 here. To check on the other 2 rows, left deflection is here, right deflection is here. At this particular point we are getting almost 0 deflection, and that corresponds to a value of 180 centimeter. I am getting 0 deflection, that is for 3 volt. Now again moving the rheostat so that the voltmeter reads 4 volt. Again find the balancing length. Again it is moving to 5 volt so that the voltmeter reads 5 volt, 6 volt, 7 volt, 8 volt, 9 volt, etc. In each time we are obtaining the balancing length, and using that balancing length we can calculate the voltage, that is V in each time, and V0 is the measured value of voltage in the voltmeter. So we are having V0 and the calculated value of V. From V and V we calculate the correction V minus V0. So that is the calibration process of the calibration part of the voltmeter, high range voltmeter. Coming to a sample set of reading in the calibration of a high range voltmeter. Here the M of the Daniell cell is 1.08 and the balancing length corresponds to the Daniell cell. We obtain 720 centimeter. So we calculate the value of potential difference per unit length, that is 1.08 by 70. Then P plus Q divided by P is 10. Then when the jockey is given contact at some point so that the voltmeter is 1 volt, we obtain the balancing length as